everyone. I am giving a brief introduction to the finite element analysis today. So there are many solve the finite engineering problems. So one of the approaches practical aspect, and second one is analytical method, and one more is numerical technique. Practical approach, there are many problems are available. The actual structure cannot be tested or analyzed by using a practical analysis, very difficult. It may not be technically feasible. So in such cases, one more method is analytical method. Analytical method, there are some restrictions are there. The standard cross section, standard boundary conditions, standard loading only you can apply. But when problems are more and more complex, then you have to go for a numerical technique, because practical approach is not feasible and analytical approach is again not possible for the complex problem. In such cases, you have to go for the numerical method, and one of the numerical technique is our finite element technique. So in general, FEM is a computational technique used to obtain approximate solution to boundary value problems in engineering. There are two types of problems. One is this is finite element analysis used for the boundary conditions or boundary value problems. So when you talk about different applications, so one of the application is the structural antenna. So when how much antenna is vibrated during when it is subject to the huge amount of loading, wind loading, whatever it may be, what is the deformation. So those things can be using finite element analysis, we can find out the deflection, deformation, stresses induced in the antenna. If you see some more applications, so like bridges. So again, this is not practically, testing is very difficult, not feasible at all, technically feasible. In such cases, we can use finite element analysis for analysis of the bridges, flyovers, elevated expressways, and especially stresses. It is mainly used for the mobile towers, bridges. Again, this can be analyzed using finite element analysis. Then one more is machine tool. Most of the mechanical engineering, there are a machine tool you have to analyze. So when machining is taking place, what is the deformation of the cutter, what is the deformation of the arbor, what is the deformation of the whole body or the column. In such cases, we can use finite element analysis to get the deformation. Then one more is finite element analysis of the whole car body. Either we can individual components also we can analyze using finite element method, but the whole car body also, when it is crash happens or because of the wind load or some other load, so what is the deformation, all those things can be analyzed using finite element analysis. Some more application is gears and gearboxes. So when one gear is meshing with another, there is a direct contact. Because of the direct contact, there is a frictional forces, some amount of thermal loadings also occur because of the continuous contact. So how much amount of load is developed, how much amount of stress is developed at the tip on the gear teeth, that can be analyzed, and we can find out what is the maximum stresses induced in the material, what is the maximum stress deformation in the teeth of the gear. So those can be found out by using finite element methods. If you see some more, whole aircraft can be analyzed by using finite element analysis. Manually, it is very impossible to analyze the whole aircraft when it is flying. So what are the wind loads, what is the structural load acting on the aircraft, all those things can be analyzed for using finite element analysis. And this is one more is pipe bend. So whenever high pressure the fluid flows through the pipes, so what is the deformation, what is the bending, all those things can be analyzed using finite element analysis. And even nuclear structure, because when it is subject to the one is structural load is acting on the nuclear structure. Then second one is huge amount of heat is carried from one area to the another area with high pressure pipelining. So then there may be some thermal analysis, there may be some structural analysis, there may be some amount of fluid analysis. In all cases, so we can effectively finite element analysis can be used. Even it can be used, not necessarily you have to use the finite element method for the only engineering the analysis. It can be used for analyzing of the sports. So when what is the amount of deformation occurs, what is the amount of vibration transferred to our hand, all those things can be analyzed using the finite element analysis. If you consider the concept, you can see. So we have the concept of finite element analysis. So if instead of analyzing the whole structure itself, we can divide the structure into smaller and smaller element. That whole process is referred as discretization process. So we can see the whole machine is discretized into smaller and smaller component. In finite element analysis, the smaller and smaller components are referred as elements. So individual elements are analyzed, and we can find out where exactly the maximum stresses are induced in the material, what is the maximum deformation in the material. We can concentrate more, we can give more emphasis for the selection of the material and more designing of those especially critical elements of the machine tools. And this is even the structural analysis of the bridges can be done. We can see here. So this is the original bridge. So there is a when after the earthquake it is collapsed. So then the whole thing can be simulated using the finite element analysis. And even we can go for other than structural analysis. There is a fluid analysis also can be used, analyzed using finite element analysis. If there is a heat transfer, especially in the case of internal combustion engine, huge amount of heat is generated during combustion process. This how much amount of heat is heat distribution in the engine. Then what is the variation of the temperature? Because of the variation in the temperature, what are the stresses developed in the material, whether it is within the allowable stresses or within the design stresses, all those things can be calculated using your finite element analysis. So it is a simple example showing this solid model. It is discretized into smaller and smaller element. We can see the first diagram represent the solid model or actual component. When you come to the second part, it is a finite element model. You can see how it is discretized into smaller and smaller element. So it is a 2D model. We can see the 2D element. It may be tetrahedral, it may be the triangular element, or it may be the quadrilateral element. Depending upon the shape of the component, we can go for either triangular element or quadrilateral element. It is an example for the discretization process. So now we can see the finite element analysis. So we have the whole plate. It is subject to the uniform loading. Then before going for any deformation analysis, we have to apply the boundary condition. On the left side, we have the fixed boundary. So our elements or the component is fixed. There is no deformation. We can see the quadrilateral element on the right side. We can see the quadrilateral element on the right side. So now, so these are dots at the intersection of the vertical line and horizontal line. So those are referred as a nodal element. One element is connected to the another element using node. So we have many element. Here we have taken the quadrilateral element, and this whole process, the dividing the whole component into smaller and smaller element, is referred as a discretization process. That means in this diagram we can identify the node, we can identify the element, it is a quadrilateral element. So we can identify the complete the structure after the discretization. It is referred as a meshing. It is the example for the coarse meshing. This is the same example we can see. So we have 2D, we have the component. The component is discretized, and we can see the quadrilateral element in our case, and this is the node. This is the node, and this is the element. This is a quadrilateral element. There may be some part, there may be triangular element also. We can, depending upon the spacing available, depending upon the where exactly the stresses are induced, or there may be some area, there may be some stress concentrated area. In those stress concentrated area, we have to go for finer and finer meshes. But if there is no stresses like area like the here, so then we can go for the coarser or bigger mesh size element. But wherever there is a stress concentrated area, in such cases we can go for the finer and finer element. So now whole finite element analysis whole process can be divided into 3 stages. So one is pre-processing stage. So when you come to finite element packages, we require some inputs. You have to provide the input to the software package. It may be ANSYS, or it may be Nastran, it may be LS-DYNA. We required the initial stages, user is giving input to the software. That process is referred as a pre-processing. In the pre-processing, we are giving material properties like Young's modulus or rigidity modulus or Poisson ratio. You are providing the geometrical model, geometrical properties like a cross-section area, length of the element. All those things will be fed into the software. Then there is one more stage. First is pre-processing stage. Next, one more stage is processing stage. So where all information will be processed. So you are going to generate the stiffness matrix for the element. From the stiffness matrix, then it will generate global stiffness matrices. Then there is an equilibrium equation. So equilibrium equations are solved to the unknown. If it is a structural analysis, the unknown is displacement. If it is a thermal analysis, unknown parameter is the temperature. So like that, depending upon the type of analysis, you are getting the unknown parameter. Most of the time you require stresses, most of the time it may be displacement. In the structural analysis, in the case of heat transfer analysis, you have to find out the temperature. So once all information is processed, then it will be post-processing, where the deformed structure and undeformed structure will be displayed on the monitor. We can see where exactly the stresses are developed, which area you have to concentrate more. There may be more stress concentrated area. More stress concentrated area is nothing but there may be more chances of the failure of the material on those particular point. So that means you have pre-processing stage. Next one is processing stage. The last stage in finite element analysis, the post-processing stage. So there are some equations used in finite element analysis. The first equation is from the Hooke's law. So Hooke's law is from the Hooke's law we can get the equation for the stress. The sigma x is given by E into epsilon x. That is again from the Hooke's law. And in finite element analysis, we have to find out the strain. Once you get the deformation, from the deformation we can get the strain. From the deformation we can get it from the equilibrium equation KQ is equal to F. We are going to discuss in the later stage. From the KQ is equal to F equation, normally referred to the equilibrium equation. So where K is the stiffness matrix, the Q is the displacement vector, and F is the force vector. From that equation, equilibrium equation, we are getting the deformation. So once we have the deformation, from the deformation we can get the strain. The deformation as per this equation, du refer to the deformation for a small distance dx. So once we have the deformation, or epsilon x, so where epsilon x refer to the strain along x direction and sigma x refer to the stress along x direction. So once we have the strain, from the strain, once we have the Young's modulus, we can get the stresses, and that is nothing but induced stress in the material. So once induced stress is calculated, we can compare induced stress with the design stress or allowable stress. Normally yield strength divided by the factor of safety. In most of normal component, the factor of safety is around taken as 2. So then, from that we can get all the deformation. You can see here, this is the element. So your member is subject to the force component F1 on one side, another side F2 is acting. So at node 1 the force acting is F1, at node 2 force acting is F2. The Young's modulus of the material is given by E, and area of the cross section of the element is given by A. All those information will be enters into the finite element packages during pre-processing stage. And this is the K matrix, the stiffness matrix for the bar element, that is given by EA divided by L, 1 minus 1 minus 1 minus 1, that is for the element stiffness matrix. From the element stiffness matrix we have to find out element stiffness matrix for the first element, second element, third element. Then from the element stiffness matrix you have to get the global stiffness matrix. Once we have the global stiffness matrix, in the similar way we require global displacement vector, we required the global force vector. Finally we have the equation KQ is equal to F. From that we can get the displacement. Once we have the displacement we can get the strain. Once we have the strain we can get the stress induced in the component or system. So then we can compare our allowable stress or design stress with induced stress. If induced stress value is more than the design stress, then you have to change the material or you have to change the cross section. So that is the conventional design process. So now we can see, so we have divided this is the bar element, we have divided the bar element into 2 elements. So one element is referred as A and one more element is referred as B. So element 1 has the Young's modulus E, element 2 has Young's modulus 2E, and length of the element is given by L. The load acting on the bar element is given by P. So in our case we have to find out what is the deformation of the material. So this is the finite element model what you have seen in the earlier diagram, that is a given diagram. So we have divided the component or bar into 2 elements. We can see here the element 1 is formed by node 1 and node 2, element 2 is formed by node 2 and node 3. At node 1 force acting is F1, at node 2 force acting is F2. So now this is the finite element model. So we can analyze the individual element. This is the element 1 and this is the element 2. If you consider element 1, the force acting is F1, element 1 is formed by 2 nodes, that is node number 1 and node number 2. In the similar way, the element 2 is formed by node number 2 and node number 3, and correspondingly we have the deformation. The deformation or displacement are given by u1, u2 and u3. So, now u1, u2 or u3 are unknown, we have to find out using our finite element analysis. So, now we can see, we have discussed about how to solve the engineering problem by practical approach or numerical approach or analytical approach. When you come to the numerical approach or finite element analysis, you have to find out the displacement, you have to define the displacement. We can define the displacement by using two types of equation. One is polynomial equations and one more is the trigonometric equation. In the most of the cases we will use polynomial equation. This is the polynomial equation is given by u of x is equal to a1 plus a2x plus a3x square. It is the second order polynomial equation, and this is you are referred u of x. This is the polynomial displacement equation along the x direction. In the similar way, we can get the displacement along y direction or the z direction depending upon what type of finite element model you are using. Either it may be the 1D element or it may be 2D element or it may be 3D element. If it is 1D element, the deformation is only in x one direction. Most of the time you are referred as a x direction. If the element is 2D element, then deformation may be along there in the x direction as well as y direction. If it is 3D element, then the deformation is there in the x direction, y direction as well as z direction. Similarly, we get u of x, u of y, u of z. So, this already you have seen. Then, so where exactly the different application of the finite element analysis? We have given some of the photos which shows what are the applications of finite element analysis. But if we broadly classify the application of the finite element analysis, so it can be analyzed for the linear static analysis. So, once you say static analysis, the load is, we are assuming that load is on the component or system is constant with respect to time. When you come to the dynamic analysis, best example is like an earthquake or moving vehicles or moving aircraft, those are comes under dynamic analysis, the where loading will be changes with respect to time. So, it may be when you come to the different types of analysis, it may be linear static analysis. Once you say linear, so now we have the deformation. When a component is subject to loading, there may be some amount of deformation. Once you say linear static analysis, once you say static, it is the loading is constant. And once you say linear, our deformation is directly proportional to force, or if you draw force versus deformation plot, it is the straight line, or if you draw stress versus strain diagram for the material, then it will be linear. Hence, it may be referred as the linear static analysis. So, again when come to the different types of the elements are considered, it may be uniaxial members. Once you say uniaxial, the loading is in only one direction, like a bars, beams, trusses, or problems under torque. And when you come to the plates, so when you come to the plate, it may be thin plate or it may be thick plate, or plate may be subject to the biaxial loading. Biaxial loading, the loading along x direction, loading along y direction. It may be subject to lateral loading or transverse loading. It may be subject to the bending loading also. It may be the combination of the lateral as well as bending load or any combination. When you come to the shells comes under 3D problems. So, again the shells, it may be depending on the thickness of the shell, it may be thin shells or it may be thick shells. So, in best example is our cylinders, when it is carrying huge amount of fluid under high pressure. So, then we have to go for the shell element, you have to select shell element. So, it may be heat transfer element also, especially it may be temperature distribution or heat flow within a body, it may be linear or it may be non-linear. Once you say linear and non-linear, again how temperature changes with respect to distance is referred as linear or non-linear. It may be linear or it may be non-linear. So, again it depending upon the material properties. Material property may be it may be material may be homogeneous, it may be orthotropic, or material may be isotropic. So isotropic material, sometimes there is a composite materials where we may not have isotropic material. The material properties are not uniform throughout the material. So no, it may not be the homogeneous material. Those are comes under materials. So there may be some amount of transient heat transfer. So that means at the beginning of the heat transfer process, there may be transit, there may be suddenly temperature increases, then it reaches steady state. Afterwards, there is no much change in temperature. Then it is referred as a, there may be, it may be steady state or it may be a transient state. It may be heat transfer analysis. Again, when you come to the boundary condition, it may be temperature boundary condition. Temperature is specified at certain location, or we can measure the temperature like a furnace wall. Inside, outside the furnace wall, we can mount the thermocouple. Inside the furnace wall, there maybe we can mount the thermocouple. We can find out the temperature. So those temperature is known at the outer wall or inside wall. Some wall, outside wall, there may be convective heat transfer, or sometimes there may be other type of heat transfer. All those things can be applied. So it may be, other than heat transfer analysis, the finite element analysis can be also applied for fluid flows and fluid dynamics. Then when you come to loading, the finite element, because once the member is subject to loading, there may be deformation. Because of the deformation, there is a strain in the body. Because of the strain in the body, there are stresses are induced in the body. The whole design, you are finding out what is the induced stress. Then you have to compare induced stress with what is the design stress or allowable stress. Just you have to compare, then you have to go for the iteration, or you have to change the material if you are not able to withstand the load, or we have to change the cross section. So types of loading, again it may be the axial loading, like a building columns are subject to the axial loading. It may be building, again the wires, the overhead telephone wires may be subject to the tensile loading, or overhead electrical cables also may be subject to tensile loading, or lift cables are may be subject to the tensile loading. Compression building columns is the best example. It may be subject to compression loading. It may be subject to shear, bending, like beams, columns, beams, building beams may be subject to the bending loading. The shaft may be subject to the torsion loading. So other than that, there may be concentrated load. If load is acting at a certain point only, or like a midpoint of the beam, so then it is referred as concentrated load. There may be surface load, like a road surface and the tire surface. There may be surface load. It may be centrifugal if it is a rotating member, and if it is gravitation, it may be subject to the gravitation loading also. So there may be, when you come to the stressor, there may be initial stress like a nut and bolt system, or velocities. Especially velocities are important when you're going for dynamic analysis. It may be thermal body when you're going for the heat transfer analysis. So you require a lot of temperature you have to find out. It may be contact loading. Just you have seen meshing of the two gears where there is a contact between one tooth and of the one gear with another tooth of the another gear. In such cases, those things are required. Then when you come to the material properties, so if the material property like a Young's model is the same in all direction, then epsilon x is equal to epsilon y is equal to epsilon z, that's equal to epsilon. So that is nothing but isotropic material. Orthotropic material, their properties are different in different direction. X direction it may have good strength, y direction its strength may be lesser. Then anisotropic material, it is totally anisotropic, its properties are totally different in different direction. When you come to the composite material, it may be multi-layered composite, or material may be viscoelastic or viscoplastic material. There may be different types of material. The finite element packages are capable of handling all types of loading. But when you come to the analytical method, so most of the time it is easy to analyze isotropic material or material with homogeneous properties. Then so it can be used for finite element analysis can be used for analysis of the aircraft or vehicle, automotives, machine tools. So again, machine tools or any of these vehicles may be made up of different materials. It may be subject to the structural loading. It may be subject to the temperature loading. It may be subject to the static loading, or it may be subject to the dynamic loading also. So when you come to the different steps involved in the finite element analysis, already we have seen some of the steps. If you summarize the steps involved in finite element method, the first one is we have the structure. You have to divide the structure into smaller and smaller element. Hence, it is referred as a finite element. That is nothing but a discretization of the domain. Once you say discretization of the domain, so then you have to divide the domain into finite element using appropriate element. So either we can go for 1D element or 2D element or 3D element, or sometimes the whole structure is axis symmetric with respect to the geometry, as well as axis symmetric with respect to the loading also, not only the geometry. Then you have to select a suitable displacement function. Just already you have discussed, either we can go for a polynomial function or we can go for the trigonometric functions. So then that is nothing but we have to define a function within each element using nodal values. Then you have to define the strains, displacement, stresses relationship. That is nothing but a stress-strain relationship we have. So different types of stress-strain relation based on it may be that's all. Then you have to go for stiffness matrix. So if initially you have to finding out the stiffness matrix, deriving the stiffness matrix for the individual element. Suppose we have divided the element into component into 2 elements, you have to find out the stiffness matrix for the element 1, normally referred as K1. Then you have to find out the stiffness matrix for the element 2, that is normally referred as K2. Then you have to combine those 2 stiffness matrix, you have to make it to single stiffness matrix, that is referred as global stiffness matrix. So in the similar way, you have to get the global force vector from the individual element force vector. You have to get the global displacement vector again from individual displacement vector before going for equilibrium equation. You have to assemble the element equations, nothing but your stiffness matrix you have to assemble, element stiffness matrix you have to assemble, element force vector we need to assemble, element displacement vector you have to assemble to get the global equilibrium equation. Then from the global equilibrium equation you have to solve for the unknown. If you are going for the structural analysis, now most of the time unknowns are displacements. Suppose node 1 displacement is u1, at node 2 displacement u2, node 2, node 3 displacement is u3. By applying boundary condition you have to find out the unknown, solve for unknown degrees of freedom, that is nothing but the displacement in the case of structural analysis, the temperature in the case of fluid heat transfer analysis, in the case of fluid flow, and in the case of fluid flow, then the different fluid parameters you have to find out. So once you have the displacement, from that by using strain displacement equation, there is a separate equation, we can get the strain from the displacement. Once we have the strain, by using Hooke's law, we can get the stresses, and once you, then everything will be post processing, it will be displayed, then you have to interpret the result. These are the different steps involved in finite element analysis. There are different advantages for the finite element analysis. So it can be, if we go for conventional analytical method, it can be used for the standard structures, either it may be uniform cross section or it may be uniformly varying sections or standard boundary condition and isotropic material, the linear analysis. But when you come to the complex, most of the engineering problems are most complex. For the most complex problems, you have to, no other option, you have to go for the finite element analysis. Especially irregularly shaped bodies. If the standard shapes like a beams, uniform cross section, etc., then we can go for conventional analytical method. But finite element can be analysis can be used for irregularly shaped bodies or any loading condition. Loading condition may be very complex. It may be in normal case, it may be simply supported beam, or it may be fixed beam, or one end of the bar may be fixed, but whole surface of the bar component may be fixed. Then boundary conditions are more complex. The loading conditions are more complex. The loading may not be non-uniform, or it may not be uniformly varying also. In such cases, we have to go for finite element analysis, has more advantages. And already it is shown, it is, you can go for unlimited boundary condition. And element size, we can go for finer meshes. Initially we can go for coarse meshes. We can increase the accuracy of the finite element solution by going by further refining the meshes. Those are referred as refined meshes. So when you come to the static analysis, we can find out the stresses. Finally, our aim is to find out the stresses, or we can find out the deflection. From the deflection, we can get the strain. From the strain, we can get the stresses during your finite element, different stages involved in finite element analysis. So when you come to the dynamic analysis, so we need to find out what is the frequencies. Just you have to compare what is the excitation frequency, what is the natural frequency. Excitation frequency should not be equal to the natural frequency because of the resonance. So huge amount of amplitude of vibration may be increases. You have to avoid the resonance phenomena in the structure, dynamic loading. For that, you have to find out the frequencies, you have to find out the modal shapes, then you have to find out the stresses as well as strain in the case of dynamic analysis. So when you come to the heat transfer analysis, you are finding out the temperature. Once you know the temperature, we can find out the heat flow rate or heat fluxes. We can find out how temperature varies within the element. Also, we can get it. That is nothing but a thermal gradient. We can find out heat flow from the convection, or it may be conduction. It may be from the radiation. When you come to the fluid analysis, important field variable is pressure. It may be temperature, it may be different coefficient. All those things can be found out or analyzed using finite element analysis. When you come to automotive industries, so you can go for static analysis, we can go for modal analysis, especially for the dynamic analysis, or transient dynamics. Whenever there is a transient, once the engine is started, the vibration level, everything will be changes, and after reach a steady state, so then it is about a steady state analysis. It may be transient dynamics. It may be some cases, if you consider the internal combustion engine, there may be heat transfer also. We can go for heat transfer analysis of the engine component, or outer body. So metal forming process, most of the outer body is produced by the metal forming process. Then when accident occurs, what is the strength when it is subject to the impact loading, then we can find out the crash worthiness of the vehicle body by using finite element analysis. Then when you come to aerospace industries, again aerospace industry, you can go for static analysis. Again, most of the aerospace components are phased during when it is flying, or then in such cases there is a dynamic analysis. In the case of dynamic analysis, so you have to go for modal analysis, or you have to find out aerodynamics also very important. There may be huge amount of heat is generated in the engine. Heat transfer analysis also required. So there are many latest material like composite material, carbon composite material, or other composite material may be used in the aircraft wing and fuselage. In such cases, we can analyze the composite material. Not necessarily those composite materials are isotropic. It may be orthotropic. Sometimes it may be anisotropic. Then aeroelasticity is also important. The metal forming, most of our aircraft outer body is formed by metal forming. Then crashworthiness, when it is subject to accident or some disaster. So whether it take the impact loading or not, that for that you have to go for the crashworthiness study. So today you have just discussed what are the different types of analysis, especially you are talking about the engineering analysis. Either you can go for especially a solution to the engineering problem. We can get it from the practical solution is one option, and second option is analytical solution is option, one more option. When practical as well as analytical solution is not possible or feasible, in such cases you have to go for the numerical analysis or approximate analysis. The finite element analysis, one of the numerical analysis or approximate analysis. So you have discussed about different applications of the finite element analysis from automotive industry to the aerospace industries. Then what are the concepts, different stages in finite element analysis. Then from the finite element analysis, what we can get the displacement. From the displacement, we are getting the strain. From the strain, we are getting the stresses induced in the body. From the induced in the body, from that we can compare our design is safe or not. Then we have discussed about different types of analysis. It may be static analysis, it may be the dynamic analysis, it may be fluid flow analysis, or it may be the heat transfer analysis. This is the brief introduction to the finite element analysis. Thank you.